Hello, my name is John Broadwell and I'm the creator of the Serial Wombat open source project. Today we're going to be taking a look at Rotary encoders and how we can use the Serial Wombat to assist your Arduino or other platform in reading such an encoder. You'll see a number of different encoders, and typically they're used for one of two purposes. One is as user inputs, typical turning knobs. You see these on the front of washing machines or car radios or any of a variety of devices where you want a knob that spins 360 degrees continuously. Typically these knobs have ticks on them that you can feel, or detents. The other application that you see sometimes is as motor measurement devices, where there'll be some kind of a spinning shaft, and the encoder will be attached to that shaft or attached via a gear set or a pulley or whatever to measure the number of turns of that particular motor. What I have here is perhaps the simplest case of a rotary encoder. It has 3 lines on it. There's 2 on here that are for a push button switch. We're going to ignore those because they don't really pertain to this discussion. But as I turn this back and forth, I can feel it clicking. What's happening as I turn it is that within this, connections are being made and broken each time I tick the rotary encoder one step forward. Let's take a look at what's actually happening. What I've got here is just an Arduino board I'm using to provide power. I've got 2 pull-up resistors that are pulling up to my positive voltage. And I've got a couple of lines here that lead out to a logic analyzer. We're going to take and ground the center wire. The other 2 pins coming out of the encoder, we're going to tie to the pull-up resistors. Now let's start our logic analyzer. We'll see on this particular rotary encoder, both of the lines are currently high. If I tick it, we see that there was a transition and it went back up. I'm ticking it clockwise. And typically with this encoder, we see that it goes down and comes back up. We saw one case over there where it's stuck. This is a low quality rotary encoder. It's relatively easy to get this one to stick between steps. So each of the turns up to this point were clockwise. Now I'm going to turn the device a few steps counterclockwise. 1, 2, 3, 4, 5. And I had a double click in there. Let's take a look at what's actually happening on those signals. Let's take a look at one of the last few clicks that we did. This is an example of the signal waveform we get when we turn counterclockwise with this particular rotary encoder. We notice that channel 5, when it goes low, the channel 7 is already low. And we notice when channel 5 goes high, channel 7 is already high. Is this consistent? Let's take a look again. We see that when this guy went low, this was already low, less some noise that we've got here. And when this guy went high, this was already high. So again, this was a counterclockwise click. Let's look at some of the clockwise ones. When channel 5 went low, channel 7 was high. When channel 5 went high, if we look within a reasonable amount of time, a millisecond or so, when channel 5 went high, channel 7 was low. So we know that for this particular encoder, when we click it counterclockwise and we look at the transitions on channel 5, counterclockwise will match. Clockwise will be opposite. By looking at these signals very rapidly, we can determine which direction the rotary encoder is turning. And for each turn, a rotary encoder gives a certain number of clicks. I think for this particular one it was 16, but that'll be published or you can figure it out experimentally. So we can tell how fast it's turning by looking at how fast these signals come, and we can tell in what direction. Let's take a look at another rotary encoder. This part is another surplus part that I've got. It has a similar rotary encoder on it. We can see it's got its 3 pins. This one is on a PCB and it pulled it out for us. Clock and DT are the lines that we're going to read. switch goes to the center one. We're going to ignore that. Ground, we know what that is. That goes to the center pin over here, probably also to the switch, don't care. The question is, what's with this plus? Why does something that just switches to ground need a plus? Well, it turns out that this particular board, if we look, they put the pull-up resistors already on board for us. So we don't need these. Let's wire this guy up and we'll see what happens. I've got the white and gray going to the signal lines, the purple going to our positive, and the brown going to our ground. We'll start up our logic analyzer again. And in this case, we can see we've got one high and one low. Actually, they're both low. They both went high. I click it again, they both go low. I click it again, they both go high. So what we're seeing is that these two rotary encoders behave differently. The first one that we had went on a good click down and then back up. This one transitions down or up for each click. So if we were doing a human user interface, we'd probably only want to read every other click on this one. On the other hand, we'd want to read every click on this one. So let's go 3 turns, 1, 2, 3 clockwise. Let's do 3 turns back, 1, 2, 3 counterclockwise. And again, look at the signals. When we went counterclockwise, we saw a drop here, and this line was high. So for this rotary encoder, the way we have it wired, when they're different, that's counterclockwise. Again, transition high to low. This was high. And it stayed that way for a pretty long time. On the other hand, we will go over here, low to high, and we're still low. We can see that we're getting quite a bit of bouncing in here. And this potentially is important, almost a millisecond worth of bouncing on this particular logic analyzer, which I found to be a bit more sensitive than what the PIC seems to be in terms of picking up interrupts and whatnot. If we look at the analog measurement, we can see that this guy is moving up and down. So what that tells us is that we're going to want to do some debouncing or some weighting on this particular pin to make sure that we don't get false transitions. You see a lot of rotary encoder projects, some professional products, some commercial products, that you turn them fast and they seem to lose ticks, or you turn them to the right and 3 out of 4 clicks work, but occasionally it'll go in the wrong direction. That's because one of two things is happening. Either they're not sampling fast enough to see this period in here between the transitions, or they're not properly dealing with the bounce noise. So, but we saw this works well. For the most part, we could definitely measure this, determine which way we're turning, and that would be fine. Let's take a look at one more rotary encoder. This one is kind of like the other one. It's mounted on a PCB board, but there's a bunch of extra stuff here. So we got what look like our normal pull-up resistors, because this one takes power and ground up here, in addition to the rotary encoder points. These guys off to the side, they've put 20 nanofarad capacitors on there. So my guess is what they're doing is using these to filter the signal that's coming off of the rotary encoder. That's one of the ways that you can help your software out, is by putting a small cap on the output signal. That'll tend to smooth those out. So let's plug this guy in and see what he looks like. Once again, this particular rotary encoder, like the first one, likes to be high most of the time. I do 1 tick, it goes down and back up. 1 tick, it goes down and back up, down and back up, down and back up. So let's click 1, 2, 3 clockwise, 1, 2, 3 counterclockwise, and we'll look at that signal. On the counterclockwise, we see the same behavior. It goes down, it's opposite, goes up, it's opposite. So on a counterclockwise click, we're getting opposites. So if we would, in our software, read when this transitioned from high to low, look at the opposite pin. If it's the same, then it turned one direction. If it's opposite, it did the other. Let's go back and look at the earlier first 3 clicks and see that that's true. Yes, when this guy transitioned, they were the same. When this guy transitioned, they were the same. Let's take a look now at the analog signals real quick. If we go up here and look in very, very quickly, we're seeing that we're not seeing any of those bouncing. And we can see the characteristic RC discharge and charge curve on the analog channels. These characteristic curves show that we're getting some nice filtering that's being done by the combination of R and C that's been selected by the manufacturer for this particular board. Hopefully they chose those values based on how long the switch bounces at a given reasonable rotation speed. If I was going to do some serious work that required me to absolutely be sure to catch every pulse, this is the rotary encoder I'd want to use. This would be pretty relevant if I was moving a motor back and forth and wanted to make sure I absolutely knew where the position of the motor was. Those RC caps, the RC filter is a good thing there. If I was doing something with a car radio, where, okay, I really want the user to be happy, I don't want it to seem glitchy, but if I miss 1 in 1,000 pulses because of, some noise or, exceptionally long bouncing or something like that, then I probably could get by without the RC caps. Let's take a look now at our Arduino demo sketch. We're going to use the circuit that you see here. We'll have a Serial Wombat 4B at I2C address 6C. Connected via I2C to our Arduino, and we're going to use 2 of the Quadrature Encoders that we saw in the earlier part of this video. The first one, which doesn't have pull-up resistors, the second one, which does. We are not using the one that has the capacitive filter, so we want to see that we can make this thing work without those capacitors. The simple encoder is connected to ground and Wombat pins 0 and 1. The one with the pull-up resistors on board is connected to ground, to VCC, and to Serial Wombat pins 2 and 3. Our Arduino sketch is very simple because the Serial Wombat is doing almost all of the work. This assumes that you've already loaded the Serial Wombat library. There's a separate video in this channel to show you how to do that if you need to. So we're going to include Serial Wombat.h. We've got a Serial Wombat that we're going to call Serial Wombat 6C based on its I2C address. And we're going to declare 2 Serial Wombat Quadrature Encoders that are on that Serial Wombat. In our setup, we'll initialize our I2C bus and initialize the Serial Wombat with a begin call telling it, hey, there's a Serial Wombat out there. It's on the I2C bus at address 6C. Then our basic Quadrature Encoder and our Quadrature Encoder with pull-ups. The basic one is on pins 0 and 1 of the Serial Wombat. The one with the pull-ups is on pins 2 and 3. And let's start up our serial at 115.2 so that we can see the result. Then we're just going to put the Arduino in a tight loop where we say, hey, read the basic Quadrature Encoder, tell me how many ticks are currently on it. Read the Quadrature Encoder that includes pull-ups and tell me how many ticks are currently on it. And then wait 50 milliseconds and do it all again. So let's upload the sketch and see what happens. Here we're using the Arduino terminal to view the results coming out of the Arduino. Let's grab the one with the pull-up resistors and crank it, and we see it goes down as we go clockwise. It goes up as we go counterclockwise. You notice that the limit on that number is 65,535. If we go above that, it goes into positives. If it goes below that, then we go into negatives. You can initialize that value to other values. Take a look at the more advanced video that's going to be linked to at the end of this one here shortly. And we can look at the other sensor. And as we see, this one is moving in increments of 2. which makes sense because we saw that there are two transitions, down and up. And it's possible for us to adjust for that using one of the parameters that allows you to say, hey, I want to read up transitions, down transitions, or both. On this one, you definitely want to read both because you get a transition per click. On this one, you'd probably only want to read up or down. On this one, you'd likely want to read just the down transition so that you got half as many. Alternatively, you could just take the number and cut it in half in software. In a future video, we're going to show how to use two serial wombats together with an I2C display to create a front panel. The advantage to this is, well, that the two quadrature encoders, the screen, two buttons, and a switch would take about a dozen wires going back to your Arduino. By using a couple of locally located serial wombats, you can limit it to just power, ground, and the two I2C lines. Look for this in the future. The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features to the Serial Wombat. If you have questions about the Quadrature Encoder feature of the Serial Wombat, leave them in the comments below. Or if you've successfully used the Quadrature Encoder feature in a project, leave us a comment, let us know what you did, how you're using it, and if you have any suggestions for improvement. The Serial Wombat open source project was created by Broadwell Consulting Inc. Broadwell Consulting Inc. provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485, as well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Questions sent to John at Broadwell Consulting about the Serial Wombat will not be returned.